Hello there, MCV4U folks. Today's lesson is on logarithmic differentiation. Now we do have a fairly big warm-up here. The first one is a reminder of how to take the derivative implicitly, and actually that's going to be a big skill that we get into today. But the second one in the warm-up is kind of the big one. It's chapter 4 in one question, except for also combining some of the things you've been doing this chapter so far. So um, hopefully you've tried these, and maybe you tried a little bit and got stuck, and then that's what we're taking up right away. So the idea of taking the derivative implicitly is we've got some relation or perhaps a function, we don't know, and it's defined implicitly. We don't have y equals, but it doesn't mean we can't take the derivative. So we take the derivative of the left-hand side here. It's a chain rule. The 2 goes down in front. We leave the inside thing alone. This goes down to 1. And then we got to take the derivative of the inside thing. Now the derivative of the inside thing is derivative of x with respect to x is just 1, plus 2y is just 2. But then this is another chain rule, right? Because y is implicitly defined, we have to take the derivative of y. This is y prime. Notice I'm gonna erase that little exponent 1 there because it kind of looks like a prime, and I don't want to get confused. The derivative of 2x is just 2. Notice I can divide out the 2's here. 2's are gone. And then so I'm just left with 1 on this side. And the idea is I find y prime, get an expression for y prime now by solving for y prime. And that's sometimes a little bit of a task. But what I'm going to do is I'm just going to divide by this bracket first. And then these brackets become not necessary. 1 over x plus 2y, subtract 1. Notice I could get a common denominator and tidy that up if I want to. And then I'm going to multiply through by a half here to get rid of this 2, or divide by 2, however you think of it. And I could get a common denominator and tidy that up if I wanted to. Dandy. That's it. That's the derivative. The next one, and I've already done this. Notice there's a question for you to try maybe after you watch the lesson, depending on how much time you have. There's not too much to do with today's homework, so you can save that for later. That's a curve sketching one that's got to do with exponential functions. So asked to graph this, use the curve sketching algorithm, and here we go. Don't look at it all at once, right? We think of the M2I2 acid and sort of think about breaking it into pieces. I always like thinking about the asymptotes first. So if I think of this, where the asymptotes are, vertical asymptotes are usually where the bottom is 0, right? Well, where is e to the exponent x squared 0? Well, never. It's an exponential function that's never 0. So there's no vertical asymptotes. It means our function's actually defined for all values of x, which is pretty neat. We don't often see that. I'm going to get to this in a second. The horizontal asymptotes, well, this is where we're thinking of the limit as x goes to positive or negative infinity. So when x gets really, really big, we have 2 divided by e to the exponent really, really big. Well, e to the exponent really, really big is absolutely huge. The exponential function, when it's positive here, it just gets enormous. So as x goes to positive infinity or negative infinity, notice that when it's negative infinity, then it's squared to become positive infinity. So this is e to a huge positive number, whether it's on the left or right. Remember that the normal exponential function is big on one side but small on the other. But since I've squared it, it's this function here is big on both sides, something like that, almost like a very, very steep parabola. But for our purposes, we can think of the horizontal asymptotes, the limit as x approaches positive or negative infinity of f at x equals 0. So therefore, y equals 0 is the horizontal asymptote. Now here's an aside. This idea of, we used to think of rational functions as which polynomial dominates. If the degree on the bottom is bigger than the degree on the top, then we know that the horizontal asymptote was zero. If the degree on the top was bigger than the degree on the bottom, well, then it would go off to positive infinity. If they were the same, we divided um, leading coefficients, and it would be like y equals 4 or something like that, whatever the leading coefficients are. Well, what happens when I have a combination of an exponential function and a polynomial function? Well, the idea is the exponential function always dominates, and it doesn't matter what degree. This could be a polynomial function that is a degree a million, and the exponential function would still dominate. So it'd be like the bottom here is still got a higher degree than the top. So here, this degree is lower than the bottom, and so then that means this would go to zero. If the exponential function is on the bottom, it goes to zero. Here, when x gets large and the exponential function is on the top and the polynomial function is on the bottom, this goes off to positive infinity. For large values of x, e to the x dominates x to the exponent n. Now, notice that it's different if I'm going to negative infinity and I'm talking about this function, because when x goes to negative infinity, this goes to zero, and I'm dividing by zero, and strange things happen, and I'd have to think about that separately. But I just wanted to point that out, that when we have an exponential function and a polynomial function that are fighting each other out to figure out who's dominating as x goes off to positive infinity, it's always the exponential function for large positive values of x. So keep that in the back of your brain, store that back there. Notice this stuff in red is my scratch work for future steps. So the future steps, intercepts, well, I'll see the table of values. So the intercepts are when x is 0 and y is 0. Well, when x is 0, I put in 0 there. E to the exponent 0 is just 1, so this is an output of 2. So 0, 2, well, that's the y-intercept. When I put in y is 0 over here, then I get this is 0, multiply by this, and I get 0 equals 2. It's impossible. So there's no x-intercepts. No x-intercepts. Which is too bad, because usually that's a big piece of our puzzle. Notice this purple stuff comes later. And so does the sign chart. Will come later. Actually, the first level in our sign chart, if I think about it, this function here, because the bottom's always positive, e to the exponent x is always positive, e to the exponent x squared is always positive, this function is always positive. So this graph is going to live above the x-axis. Okay, so then I'm ready for my mins, maxes, and increasing and decreasing intervals. Take the derivative. This is just a chain rule, right? So the 2 hangs out front. The derivative of the exponential function is just the exponential function, but then I got to take the derivative of the inside thing. This thing here is the derivative of negative x squared. The 2 comes down, so on. And then I'm analyzing where it's, I tidied up for a step, and then I analyze when this is equal to 0, because when the derivative is equal to 0, that's when I get my critical points. So I'm thinking of this as kind of like 2 factors here, and it's the product is 0. Well, when does this equal 0? Well, never. No solutions. This adds no information to our graph at all. But here I get x equals 0 is a critical point. So I put x equals 0 on my sign chart, and then I analyze it for values on either side of 0. Also notice f prime at x is defined for all x. There's no spots where the derivative doesn't work. So that means there's no critical points that way where f prime at x is undefined. So no problem there. So look at the sign chart. I can look at this function, my derivative function. I know it's 0 there. For values less than 0, less than 0, I'm going to have, I had this backwards. Good thing I checked. This was backwards, isn't it? All right. For values less than 0, right, x is negative. Negative 4 times a negative number. This would be positive. This is always positive. So positive times positive, this is going to be positive. So it's increasing for values of x less than 0. and then decreasing for values greater than 0, because values greater than 0, this thing will be negative times a positive is a negative. This is always positive, so a negative times a positive is going to be a negative. And then I see it's increasing up to 0 and decreasing after 0. Don't worry about the sketch yet. That'll come after we've painted the entire picture. So what's the rest of the picture is to look for the concavity and the points of inflection. So I take this, and it's a product rule now. So I take the derivative. Take the derivative of the first part is just -4. Write down the second part. Write down the first part. Take the derivative of the second part. The derivative of the second part is the function itself. Then the derivative of the inside part. Tidy it up because I see a common factor. There's a common factor of -4 and e to the exponent -x squared. So that comes out front. And then what's left over, I get 1 minus 2x squared. And if I'm interested in points of inflection, then I want to know when this is equal to 0. This part's never equal to 0, and this part is equal to 0 in 2 spots. This goes to the other side, divide by 2, square root. I get 2 points of inflection at 1 over the square root of 2 and -1 over the square root of 2. So I put those on my sign chart in purple. Analyzed where that second derivative is positive or negative. And so notice this is always negative. For values that are more negative than -1 over the square root of 2, then this part is going to be negative. So I'd have negative times a negative, which would make this a positive. So I can say, therefore, concave up on those values. On x goes from -infinity to -1 over the square root of 2. But then after that, it's going to be right until I get to the other point of inflection. It's going to be concave down because this is always negative. -4 times something that's positive. This is always negative, and then this is a value that's less than 1 over the square root of 2, that, like 0. 0 is my favorite, which would make it positive, right? This thing is going to be 1 minus a number that's smaller than 1, as it turns out. So that's going to be a positive number. And so negative times a positive is a negative number. And then similarly, I could get those values out there. And notice, if you don't like thinking of, what factors are negative and positive, you could always just do a test point and jam those in there. And then I also get that x is concave up on these numbers as well, and concave down on the values in between, right? -1 over the square root of 2 to 1 over the square root of 2. And then I put those things together and I get that sketch. Notice that I had to put in my points of inflection to figure out what their y values were, so I could put those on the graph. There's the points of inflection, and this should, if there's concave up, concave down, concave up, there's my maximum, right? My maximum there that I knew was coming. And this should look has a familiar shape for anybody who's taken data management. This is the bell curve, or a version of it, also called the normal distribution for folks that have taken data management. So, but for us, it's just another graph. All right, well, what a warm-up that was. Now, these questions are important because of all the skills that we use. Today's lesson is a little, well, maybe not less important, but certainly not, as the questions aren't as much work. So we'll get to that. We'll get to the actual lesson in part 2.